Let's talk about training large language models at low precision. Today, most LLMs are trained using 32-bit or 16-bit floating point precision. That means each weight in the model gets 16 or 32 bits to express itself, a whole lot of room for numerical nuance and accuracy, but also a whole lot of computational cost. Think energy, time, memory, and ultimately money. Quantization, so squeezing model weights into low precision formats like 8 or 4-bit, is already a commodity for LLM inference. 2-bit and even binary quantization exists to run models cheaply after training. But what if we told you that you could squeeze each weight and activation into just 4 bits during massive LLM training with barely any performance loss? That's exactly what this new paper explores. It's called Optimizing Large Language Model Training Using FP4 Quantization, and it pushes the boundaries of what we thought was possible when it comes to ultra-low precision training. It's kind of a big deal because over 90% of the training cost for LLMs comes from one operation, matrix multiplications. And matrix multiplications with 4-bit numbers, that's fast. It means more multiplications per GPU core, better cache usage, lower memory bandwidth, and potentially huge speedups if the hardware can support it. But of course there's a catch. Reducing precision down to FP4 introduces massive quantization error. Naively training an FP4 fails miserably, just look at the green loss curve. So how did these researchers get it to work? And not just kind of work, but match 16-bit precision, sometimes even outperforming it on real benchmarks. In this AI coffee break, we'll explain how it's done, because training large language models in low precision is a game changer. Faster, cheaper, greener. But what if you could upgrade your skills just as efficiently? That's why Simplilearn impressed me. It's one of the top online platforms for tech and business education, packed with hands-on programs in AI and machine learning. And now they've launched SkillUp, a completely free learning platform with self-paced courses in AI, generative AI, data science, cloud computing, and more. Personally, I so much like their course on Hugging Face, a must-know Python library if you're working with LLMs, whether in industry or at university. And their course on retrieval augmented generation is also a favorite because, let's face it, Gen AI without RAG just doesn't cut it anymore. And in the same course, you even get to learn about the LLM transformer architecture. Whether you're a student, dev, or just AI curious, SkillUp offers self-paced courses crafted by industry giants like Google, Microsoft, and AWS. You'll also find awesome free resources on career paths, salaries, interview prep, and job-ready skills. And yep, you even get a free certificate when you complete a course. So if you're serious about getting into AI or ML, definitely check out SkillUp by Simplilearn. Hit the link in the description or pinned comment to get started. Big thanks to Simplilearn for sponsoring this video. Now, let's dive into FP4 training. Why are people so excited about low precision training in the first place? Well, training a large language model, think of billions or even trillions of parameters, is expensive in terms of compute and energy and money. Every parameter, every activation, every gradient, they are all just numbers being shuffled around in GPUs. And the fewer bits you use to represent those numbers, the faster and cheaper the training gets. With the right CUDA kernels and hardware, you can multiply many 4-bit numbers in the time and memory it would take to process just one 32-bit pair. That's a huge gain in throughput and efficiency. Let's say we start with FP32, 32-bit floating point precision. That gives you about 4 billion possible values to represent a single number. It's super precise, but also heavy. So researchers moved to BF16. This uses just 16 bits, which halves the memory use and increases training speed, especially with modern GPUs like NVIDIA's A100 or H100s that are optimized for 16-bit compute. Then came FP8, 8-bit formats with limited range and precision, but even faster performance. This format is so slim that you can only represent 256 values. For example, you cannot even represent 42 exactly, but it's 40, which is the closest number to 42 in this representation. If you design your model and training pipeline carefully, you can train models in FP8 and get similar accuracy to FP16 at a fraction of the cost. Achieving such low precision typically involves quantization during training. Model weights and activations are taken from their FP16 representation and are converted to the limited range of 8-bit values. We use the FP8 format to make the forward pass during training. Then during the backward pass, the model weights are updated in their FP16 version. For the next training iteration, the FP16 version gets again quantized to FP8, the forward pass is made, the loss gets computed, gradient weights and updates are done in FP16, and so the cycle repeats. But my favorite approach to FP8 training is the one used in the UMUP paper, namely, instead of relying on post-factum rescaling, where you first multiply weights and activations from the previous layer and then try to squash the resulting activations back into the FP8 range, UMUP does something smarter. Design the model such that the activations naturally stay within the FP8 range right from the start. In other words, UMUP parameterizes the weights such that it's mathematically guaranteed that the activations already lie close to the center of the floating point format dynamics range. That means that most of the time you can just run to float 8 and you're good to go, no need for complicated dynamic rescaling after the fact. This is also super useful in post-training quantization, where too large activations are also a huge problem. But okay, since FP8 training has been conquered, what about FP4? Well, so far, training in 4-bit precision was an entirely different beast. Because training is sensitive, the model is constantly adjusting weights based on tiny gradients. Low precision formats can lose that subtlety. I mean, think about it. The E2M1 FP4 format can only represent 16 distinct values. 16. What you see here in this FP4 lookup table is all you get for any number in your model. Compare that to billions of values in FP32 and you start to see why this is hard. You take the high precision representation on the left, take the maximum values in there and scale all the numbers to the range -6 and 6. Then you snap the values to the nearest value available to you in the FP4 lookup table. You can see many different values of the original tensor end up having the same value in the quantized tensor. Even worse, many quantization functions are non-differentiable, meaning you can't even backpropagate through them properly. So most people assumed FP4 training was either impossible or unstable, but in this paper, the authors show how to actually train a large language model in FP4 by combining quantization strategies with hybrid precision for some parts of the training loop and tricks like gradient estimators that let you backpropagate through quantization. It's not just theory. They trained a 13 billion parameter LLaMA model on 100 billion tokens, and it worked. So now that we've seen the bigger picture, let's get specific. How exactly do you train an LLM in just 4 bits? The authors target the biggest computational bottleneck in training, matrix multiplication. These account for more than 95% of the total compute, so the author's idea is simple. Perform all those matrix multiplications in FP4. That means that the weights and the activations need to be quantized to FP4. But not everything can be FP4. The sensitive parts of training like weight updates, optimizer states, and gradient accumulation are still done in FP8 or FP16, where you need a bit more precision to maintain stability over time. So overall, this counts as a mixed precision training setup. At each step of training, the authors quantize the model weights to FP4. For this, they used the appsmax function, which scaled all values in the tensor relative to the maximum absolute value in the tensor. This quantization is done at every training step and not just at the beginning of training, because the authors computed the weight updates in the backward pass on an FP16 master copy of the weights, so they needed to re-quantize the weights with the appsmax to FP4 for the FP4 version which is used in the forward pass. A master copy is needed because FP4 doesn't have enough precision to store the tiny changes that happen during weight updates. These updates are often small, floating point values, and if you try to apply them directly to FP4 weights, they'd get rounded off and lost, which would break learning. So instead, the model keeps an FP16 version of the weights behind the scenes, and during backpropagation, it applies the updates to this high precision copy. Then, for the next forward pass, it requantizes the updated weights back to FP4 using the appsmax function. This dance to compute in FP4 for speed and update in FP16 for stability is one of the key ideas that makes ultra-low precision training actually work, but this alone isn't enough. Even with careful quantization of the weights, there's still one major hurdle, namely the activations. As it turns out, activations are much harder to quantize than the weights because it's impossible to know ahead of time what the weights multiplied to the input will produce. So activations contain outliers, values that are so much larger than the rest. These outliers stretch the dynamic range, making most of the other values appear small and squished during quantization. And in FP4, that means that most of your activations could just round to zero, which is not ideal. So the authors do outlier clamping and compensation, in which they identify the top 0.1% of the activation values in the activation tensor and clamp everything above that threshold. That narrows the dynamic range, so the appsmax quantization works better, but wait, we still need the information from those outliers, so they store the residuals, the difference between the clamped and the original values, in a sparse matrix, and compute the next layer's computation with the residuals separately in high precision. This adds minimal overhead because the delta matrix is sparse, but it helps preserve important information. That's how they keep FP4 activation stable, clamp the extremes, and compensate for them separately. The last ingredient for making FP4 training work concerns the backward pass. Quantization functions such as the appsmax are not differentiable, and that's a huge problem for backpropagation. A commonly used workaround in literature is the straight-through estimator, or STE. You pretend the quantization didn't happen and compute the gradient of the weights with respect to the loss, like the appsmax function was never there. But this is crude, especially at low bit widths like FP4. It leads to poor convergence and unstable training like in the green curve. So the authors propose a smarter solution, namely a differentiable gradient estimator. It works like this. During the forward pass, they still use hard quantization to keep things efficient. But in the backward pass, they apply a smooth differentiable function that approximates the quantization operation. So instead of abruptly snapping a value to the nearest FP4 level, as the appsmax function does, this approximation for the appsmax nudges values just a bit towards their FP4 levels. Think of it like sliding down a ramp instead of falling off a cliff. It's not exact, but it gives gradient descent enough of a signal to know into which direction to update the weights. And the result? Much better gradient estimation, especially for the weight updates. So putting it all together, matrix multiplications are run in FP4, weight updates, gradients, and optimizer states are done in FP8 or FP16, quantization uses the non-differentiable appsmax in the forward pass, but the backward pass pretends it was a differentiable approximation that produced the activations instead. Activations are tamed with outlier clamping and sparse compensation. And the result? The authors trained LLaMA models on 1.3 billion, 7 billion, and even 13 billion parameter sizes on 100 billion tokens using this FP4 training framework. And training curves almost look identical to BF16. Now, onto real-world tasks. The models were evaluated zero-shot on a wide range of benchmarks. Across these, FP4 consistently matched or even slightly outperformed BF16. But overall, the average accuracy across 9 benchmarks was 54.95 for FP4 and 54.44 in BF16 for the 13 billion size model. This isn't just good enough, it's competitive. So what's the catch? Well, they didn't run this on actual FP4 hardware. Since no GPU currently supports native FP4 tensor cores, the experiments were done using FP8 hardware emulating FP4 which means no speedups were realized yet. In fact, emulating FP4 onto FP8 hardware is slower due to also the custom casting and lookup operations. But here's the exciting part. NVIDIA's upcoming Blackwell GPUs will support native FP4 compute, so the moment this hardware arrives, this kind of training could actually double throughput compared to FP8 and reduce memory and energy use even further. All in all, this could make large-scale training accessible to smaller labs, startups, or even universities. By showing that training in 4-bit precision is not only possible but practically viable, it challenges our assumptions about what's needed to train powerful models. And who knows, in a few years FP4 could be the new BF16. If you enjoyed this deep dive into the world of ultra-low precision AI, give us a thumbs up, subscribe for more research breakdowns, and thanks for watching, and see you next time for another AI coffee break. Okay, bye.